Hi class, it's Brian. I wanted to show you some of the tools in Statcrunch that are going to be useful for you on this week's module. And so I'm going to run through some of the homework problems and use them as examples. I know your homework problems are going to be very, very similar, but it's okay. So, okay, I'm going to skip a few of them, but I'm going to go through probably most of them. Starting with 3, we're going to test whether, so we're just given some data. There's no context, there's no story. We're sampling from 2 populations. We're trying to conclude something about the difference in the 2 population proportions. So we're testing whether P1 is greater than P2. First off, the correct null hypothesis and the alternative. The null hypothesis is going to be that P1 equals P2. The alternative is this hunch that we're testing, P1 greater than P2. And, okay, the test statistic. Now this we're going to get from Statcrunch. So open up Statcrunch, proportion stats, 2 sample with summary. We don't have the data, we just have the summary. And so let's see what we've got. I'm going to try to make it visible. Okay, so we're just going to be using this information here. The number of successes from sample 1, 127 out of 241. From the second sample, we have 135 out of 309. Oops, 309. Make sure I didn't make any typos. Okay. And the null and the alternative. The null is that the 2 proportions are equal. The alternative is that the difference is greater. Now notice this difference in how it's written. P1 equals P2 as opposed to P1 minus P2 equals 0. If you think about the equations, they're actually saying the same thing. It's just their different way of writing it. And P1 greater than P2 is the same as the P1 minus P2 greater than 0. If you consider like subtracting P2 from both sides of the equation or the inequality, you'd get P1 minus P2. At any rate, let's click compute and get our results. We got a T statistic and a p-value. That's it. That's all we need. The Z statistic, 2.098. Rounded up, it's going to be 2.10. And the p-value to 3 decimal places, it's 0.0179, rounded up to 8. That's a pretty small p-value. We're doing this at a alpha at 0.10, so that's the p-value is way less than that, which means that's very, very strong evidence in favor of the alternative. So we reject the null because there is sufficient evidence that the P1 is greater than P2. Okay, super. Okay, now confidence intervals for a difference of 2 proportions. Let's go back to it'll be found under, again, proportion stats, 2 sample with summary. So once again, I'm going to type in what's given to me. It's going to be the number of successes, 375 out of the first sample size, 521, and 404 out of 577. And we're doing a confidence interval, and we just have to set the confidence level 90%. Okay, 90%. Compute. Look at that. Isn't that beautiful? We've got the lower limit and the upper limit. Type it in. -0.025. Let's see, 3 decimal places. All right, that looks good. To 0.064. Rounded up to 0.65. 0.25, 0.65. Perfect. All right. Moving on, let's see. If I want to look at 6, let's go to 7. I mainly want to show you stuff in Statcrunch. This is a great one. Okay. Notice that this one you're given some data, and so rather than typing it all out and doing the calculation manually, you can click this little button here to copy this data into a Statcrunch table. Open in Statcrunch. This is a beautiful feature. So you get a little Statcrunch window with your data. It's going to be in columns. Just wait a moment or two, and it'll pop up. Anytime you see this little button next to a table of data, you have this ability to open it in Statcrunch, and you'll get a little data set here. Okay, now let's look at the question. Why are these matched pairs? Look at the story. Muzzle velocity in feet per second of shells fired from a gun. For each shell, 2 measurements of velocity were recorded using 2 different measuring devices. So because this, the 2 measurements are taken on the same round, each round being a single bullet or shell, that's why they're matched, because it's the same bullet measured by 2 different devices. Okay? Now, let's do this. Let's see. We want to do a hypothesis test on the difference of the means. So oops, this is the wrong Statcrunch window. This is the one I want. Okay. This is going to be under stat. Because we have a small sample size, it'll be a T statistic, not a Z statistic. T stat paired. All right. This is great. Data, so you can see my sample 1 is in column A. Sample 2 in column B. Where, group by, leave them blank. Don't need to save the differences. We want to do a hypothesis test, and let's just check what are we testing. Is there a difference? Okay, we're not checking if one is less than the other. Is there a difference? So our alternative hypothesis will be not equal to. It's a two-tailed test. And we got our data. Okay, we have a p-value of 0.1682. And if we look back at this test, it says use an alpha level of 0.01. So this p-value was much, much higher than 0.01. That means that the evidence is, there's really not a lot of evidence to support the alternative. The data collected, it lends us to believe that the null hypothesis is probably true. So we do not reject the null. Okay, let's do a confidence interval. All right, so if you go back here, hit options, edit, we can change this to, instead of doing a hypothesis test, do a confidence interval, and we can just set the confidence level, 0.99, and hit compute, and it's there for us. We don't have to do any calculation. Okay, so let's see. So it's negative 12.4968497. Got to round it up. 5.363. I have to round that up too. 5.364. Looks good. Double check your numbers. Okay. Great. Okay, so let's interpret this. The only way to interpret confidence intervals is to say it like this. I am blank % confident that the mean whatever is between this and this. So I am 99% confident that the mean difference lies in the interval above. That's exactly how you want to interpret a confidence interval. All right, fantastic. Okay, now let's see. Number 8 is pretty much the same. We have paired samples. I'm going to skip this. Save. Don't worry about this. Is just because I did it again, and I did it in a previous recording that had a glitch. So, all right, let's see. This looks again like the same. Let's see. Using. Oh, this is another paired sample hypothesis test. It's more of the same. Okay, this is good. This is different. Now, we've got, assuming both populations are normally distributed, construct a 95% confidence interval about mu1 minus mu2. the mean of the experimental group mu1 represents, okay. All right, so this is very bare bones kind of problem. You don't have a story or any context. All you've got is the data, and you're trying to determine whether there is we're doing a confidence interval for the difference of the population, the difference in the population means. So since the sample size is only 30 and 20, we're going to use a t interval rather than a z interval, especially because the sample size is 30 and 20, and because we don't have population standard deviations, we don't want to use the z intervals. You are going to use z stats if you have if you know for a fact that the population standard deviations. So anyway, there's no harm in using a t interval instead, because as the sample size grows, then the t distribution looks just like the normal anyway. Okay, so we've got the summary data, and I'm going to do T statistic 2 sample summary data. All right, so let's look at this next to the data here. Sample 1, we've got 30. Oh, I'm sorry, that's the mean. I want to put the sample mean, which is the 45.9. Sample standard deviation, 5.7. And the sample size of 30. All right, second sample, there's 40.8. Standard deviation of 13.6. And then the sample size of 20. All right, so I'm doing a confidence interval, and I want to do a 95% confidence interval. Now this option about pooling variances means if under the no, that's not going to affect our confidence interval, but for hypothesis testing, if the null hypothesis is that the two populations are actually one and the same, then you would essentially calculate what's called a pooled variance. You would take the two sample standard deviations, and you would kind of merge them together into one other number, which would be the pooled standard deviation. It's kind of like, if the null hypothesis is that the two populations are one and the same, you might as well take both samples as being one large sample from a single population, and you can get a better calculation of the sample standard deviation by pooling the variances together. Anyway, that only applies to hypothesis testing. For confidence interval, that's not applicable, so it doesn't matter. I'm just going to compute this, and okay, I've got my numbers there, lower bound, upper bound. So let's type it in, -0.49, 2 decimal places, that's all I want, to 10.69, 10.69. Oops, look at that. I put in an apostrophe, 10.69. Yeah. What's it doing? I think that I may have accidentally. I think I should have had this unchecked. Let's try that. Yeah, okay. Don't have that checked. It's going to mess up your calculations for confidence intervals. So let's go back. -1.54 to 11.74. Excellent. All right. Okay, let's look at some of the other ones and see what other problems there are. the data table. Okay, so what do we have? Sample data. Okay, so they're just giving it to you right like this. Let's see. This looks like it's the same problem. I'm going to skip it. You can follow the technique. Oh no, this is for a hypothesis test. So this is good. Let's do it. Okay. So first off, we're checking whether mu1 is less than mu2. So the alternative has to look like mu1 less than mu2. The null is going to be that they're equal. It's exactly that first one. Okay. Now let's go back to Statcrunch and calculate this stuff. So we're going to do a T statistic, a 2-sample T statistic with summary. So once again, we have the sample means. Just type it all in. 1.103.4. Sample standard deviation 12.2. Sample size 32. Second one 114.2. 13.3 and 25. Okay, I'm not going to pool variances. I'm going to let's see. The null is that they're equal, and the alternative is we're going to have this less than sign to match what we've decided already. And I'm going to compute. We've got a p-value. Our p-value, you can see it. Okay. T statistic is here. 0.0014. So 0.001. I'm rounding. Good job. And we want to interpret it. So p-value is tiny. It's way less than our alpha. We want to reject. There is sufficient evidence. Reject. There is sufficient evidence. All right, cool. Oh boy, story. Okay. In baseball, League A allows a designated hitter to bat for the pitcher, who is typically a weak hitter. In League B, a pitcher must bat. The common belief is that the results in League A teams scoring more runs. In interleague play, when League A teams visit League B teams, the League A pitcher must bat. So if DH, designated hitter, does result in more runs, it would be expected that League A teams will score fewer runs when visiting League B parks. Okay. To test this claim, a random sample of runs scored by League A teams with and without their designated hitter is given. Okay. The data table. We'll look at that data table. So it's giving you the full data set, but it's also giving you the summary statistics. This is nice. We don't actually have to deal with this data table, but you could actually open it up in Statcrunch if you want to. We don't have to though. Yeah, let's do it. This way I don't have to type anything in. It avoids the possibility of making a typo, and it's maybe a little bit easier, especially because I don't have to count the sample sizes. It's just going to be done automatically. Okay, so we're once again going to it happens to be that we have the same sample size for each one, but it doesn't mean we're not pairing things up. So it doesn't say that it's the same team against the same opponent or anything like that. So there's no reason to assume that these samples from League A and League B are dependent in any way. So we'll take this as an independent sample comparison. So 2-sample T-stat with data. League A, League B. Where? Don't worry about that. Doesn't matter. Pool variances? No, we're not going to pool variances. Okay. Now, what are we trying to check? We're determining whether the claim is that League A teams will score fewer runs when visiting. So the mean for A is less than the mean for B. That's our claim. So that's going to be our hypothesis, our alternative hypothesis. Yeah. Hold on. Hey, we all make mistakes. If to test this claim, okay. Does the designated hitter result in more runs? Oh. Okay. Okay, sorry. So I misread that. Does the designated hitter result in more runs? So it's going to be the greater than. Mu A greater than mu B. That is to say, when League A is only playing League A, the mean is greater than when League A is playing League B. Okay. So now, back to this. Okay, we've got our data in there. We've got our hypothesis test. Let's fix this. It's a greater than sign. And we're going to go compute and see what we get. We got a p-value, 0.0165. That rounds up to 0.017. And what do? Our alpha level is 0.05. We had a p-value 0.017. It's less than alpha, so we do reject. There is sufficient evidence that the games played with a designated hitter result in more runs. That's what B is saying, and that's what we want. Excellent. I'm going to just see if there's anything else we want to look at. Confidence intervals for, let's see, a difference of population means. Let's see. We can do this here. Let's see. So a sample of 40 adults with no children, and then a random sample of 40 adults who do have children. Okay. So let's make a confidence interval for this. It's under stat. Let's just talk about what type of interval it is. So we have 40 adults with no children under the age of 18 years. We have a mean and a standard deviation. We don't have population standard deviations, just sample standard deviations. I'm going to go with a T statistic, not a Z statistic, for a 2-sample T statistic with the summary data. So we've got the sample mean for sample 1. This is the first group of adults, is 5.97, standard deviation of 2.44, and the sample size was 40 adults. For the second group, it says it's 4.08. We have a standard deviation of 1.69, and the sample size also 40. Okay, I'm not pooling variances. And let's see, we want to do a confidence interval, and we want it to be a 90% confidence interval. And that's it. 90%. Compute. Let's check it out. So, looks like the difference between their leisure time, the mean difference, we're 90% confidence the mean difference is between 1.10 hours and 2.67. So, 2 decimal places. 1.1, I have to round it up to 1.11, and then 2.67. Isn't it so satisfying when it tells you good job? Okay, so no, we don't say that there is a 90% probability. We say we are 90% confident. Okay, there is 90% confidence that, let's see, the difference in the means is in the interval. And because this difference, because the difference is, we're 90% confident that this difference is between 1.11 and 2.67, that means we can, the data is significant, there's significant evidence to show that, yes, adults with no children under the age of 18 have more leisure time than adults who do have children under the age of 18. It seems like a pretty obvious conclusion. I mean, you don't need to collect data to know that. But yeah, there is a significant difference in the number of leisure hours. And okay, we're gonna skip 14. I think you'll find that it's very straightforward. So anyway, I hope this is useful to you guys, and I will check in with you more for more videos as there's more features in Statcrunch I want to demonstrate for you guys. And I wish you the best of luck in this week's module.